Welcome back. I hope you had a good spring break. Let's get started by looking at the finite state machine. Specifically, let's explore the state diagram. The last time we met, we described a finite state machine that looked something like this. We start with a cloud of combinational logic that has inputs and outputs. To that combinational logic, we add a series of flip-flops which hold the state of the machine. The input to the state registers is the output of the combinational logic, and the output of the state register goes back to that same combinational logic. If we're more precise, we would call this the state, and we would call this state next, with the understanding that the state registers are activated by clock, and the contents of state next will be transferred to state on the rising edge of clock. For our purposes, we'll assume that these state registers are the type D flip-flop. The schematic symbol for that D flip-flop looks like this. Here's your D input, Q output. There may or may not be a Q not output, and there will certainly be a clock input, which is this little triangle here. This particular example is a rising edge triggered flip-flop, where on the rising edge of clock, we would say that Q is assigned the value of D. This may look backwards, so let's go ahead and write that out. We would say Q is assigned the value of D. As an example, consider this circuit. Let's start with a 555 timer, which will give us a square wave at whatever frequency we desire. Feed that into a flip-flop. Actually, let it go in on the clock input. And then let's do something interesting here. Let's take and connect D to the Q naught of that flip-flop. Earlier, we said that Q is assigned the value of D. We also know that Q naught takes on the value opposite of Q. We can show that on a timing diagram like this. Here is the clock signal coming from the 555 timer. We'll assume Q has an initial value of 0, which means that this will be a 0 output here, and this Q naught will be a 1, which means on the rising edge of clock, this 1 is transferred to D, which is then transferred to Q, changing this to a 1 and this to a 0. Here is Q. Here is our Q naught. We assume Q starts at 0 and Q naught starts at 1. On the rising edge, they will transition. They will stay there until the next rising edge, at which point this 0 is now transferred to D, which is transferred to Q. So the signals will transition like so. They will stay there until the next rising edge. You can see that this circuit is a frequency divider. It's a divide by 2 operation. On every rising edge of clock, the Q outputs will toggle. So if this is a 1 kilohertz signal going in, it will be a 500 hertz leaving. As I said, that is an example of how a data flip-flop might be used. Moving back to our state machine, we would likely see several flip-flops tied together. For example, if we assumed that this was 3 lines, that means there would be 3 data flip-flops, which will be sketched mirrored because our signal is flowing in that direction. We'll put the data input here and the cue here, the clock signals here. Let's tie all of the clock signals together. And now here are the 3 state next inputs, and here are the 3 state outputs. Just in case you missed it, our finite state machine contains memory to hold the state of the machine. Speaking of states, the last time we met, we drew a diagram that looks something like this. We defined a state 0, a state 1. If the condition is correct, we will transition from state 0 to state 1. We stay in state 1 until some other condition has come true. And of course, once we're in state 0, we'll stay in state 0. A good example is a 2 push-button system where you have start and stop. If the start button is pushed, you transition from state 0 to state 1. You can still push the start button if you like, although nothing will happen. However, if you push the stop button, you will transition from state 1 back to state 0. Actually, that's a bit simplistic. We might want to put an AND operation here, making sure that stop is equal to 0. That little clause will keep you out of trouble, because if the operator pushes the start and stop button at the same time, you do not want to be running around inside the circle. Should the operator push both buttons, you would much rather stay right here in state 0. By the way, these states can have many different names. In this particular example, you might want to call this the stopped state, and you might want to call this the running state. At any rate, this graphic is called a state diagram. The circles identify the states, and the lines are the transitions. Let's look at another example. This time, let's assume we're looking at a garage door, which has 2 buttons, a button for up and a button for down. That garage door will ride on a track. To this track, we'll add 2 limit switches. The first will be limit switch up and limit switch down. As a first approximation, let's assume 4 states. Call this first one door down, moving up, door up, and of course the final state is moving down. Let's assume the door is in the down position and that the operator pushes the up button. We will transition from door down to moving up, right? Because it takes a certain amount of time for the door to actually move from one position to another. When the door has moved all the way up, it will push against this limit switch. On our state diagram, that looks something like this. So limit switch up transitions the door from the moving state to the door is resting in the up state. Should the operator select the down switch, the door will start its transition down until this limit switch is pressed, in which case the state machine will transition to the door is down state. So this is limit switch down. Of course, it's more complicated than this. For example, if the door is moving up and the operator pushes the up button again, nothing happens. However, if the door is moving up and the operator pushes the down button, we'll transition to the door moving down. Or if you're in the moving down state and the operator selects move the door up, you'll transition into the moving up state. And there are a few others. If the door is up, we don't care how many times that button gets pushed. If the door is down, we don't care how many times the down button is pushed. And of course, if the door is actively moving down, we don't care how many times the down button is pushed. Anyway, that'll get us started. Although I would argue that this particular example is woefully inadequate because we should add a stop button to this system, and it should include an obstacle detector. Here's another example. This time it will be a water pump with a pressure sensor and a timer. To get started, assume 3 states. Let's call the states full, filling, and fault. Starting from the happy state of full, the machine will transition to filling if the pressure sensor detects a low pressure. When the pressure increases, the machine will transition back to full. However, while the tank is filling, if it does not fill within a prescribed time, for example, if it does not fill within 2 minutes, the machine will enter a fault state. Notice that there are no lines leading from the fault state back to the other states. That implies that the machine will stay in the fault state until it is power cycled by an operator. By the way, this is a horrible design for a real-world system. You should never use a single pressure sensor, right? You can't just say if pressure equals, say, 40 psi. Because what will happen is any little tiny disturbance will cause you to transition states. And as soon as the pump turns on, you'll transition back. So you end up with a system that chases its tail, that toggles rapidly between the 2 states. No doubt this is going to shorten the motor's life, and it's going to tear the contacts out of the switches as well. I'll leave it to you to do your homework to find out what the word hysteresis means and how that can help us. Now here's a question for you. How many flip-flops do you see in this state diagram? Remember, the states are identified by the circles. So there's 1 state, 2 state, 3 states. We want to know how many bits or how many flip-flops are required to encode the state. That's actually an old question. We first encountered it as a decision tree. Let this be state 1, state 2, state 3. We can then prune this particular branch off. At any rate, this requires 2 questions. So we have 1 bit to determine which direction, so 0 or 1, and then we have a second bit or a second question to determine which branch we take from there. So in this case, we need 2 bits. Or if you recall, that was a log base 2 of 3. which gives us 1.59. Round that to the ceiling gives us 2 bits. Here's another example. Suppose you were working on something that required 60 states. How many bits would you require? Well, same thing. So log base 2 of 60, which is about 5.9, round that to the ceiling, gives you 6 bits. Moving back to flip-flops. We end up with a structure that looks like this, where these are the actual state outputs, and these are the state next inputs. By the way, nobody likes drawing flip-flops that way. It's so much easier to sketch a register. Data input, Q output, clock. The difference is that we use the slash notation. All right, so that is a 6-bit register. 6 flip-flops all in a row working together on a common clock. So we could say that these two are equivalent, with this one being much preferred. Actually, this is a concept that's going to become more and more important to us as we move on, because we're going to move into hierarchical designs. As an example, consider a device that counts from 0 to 60 and then resets itself. We would call such a machine a modulus 60 counter. The core of the counter is a register, which is nothing more than a bunch of data flip-flops. The register is driven by an adder. We'll put a plus symbol here to remind us that that's what's going on. To this adder, we're going to wire in a constant of 1. Make a little note here that that's a constant. The other input to that adder is the output of the registers. That's actually a vector or a bus that is 6 bits in width. Let's give ourselves a little more room and add a reset block. This reset will monitor the output, and when the count reaches 60, it will reset the registers back to 0. What do you think? Does this look like our state machine? If we took all of this stuff here and we call that our cloud of combinational logic, and if we called this block here the memory, I think you can see it a little more clearly. This piece here holds the state, which is just another word for count in this particular case, and this line right here holds state next. For example, if state is equal to 19, that means a 19 will appear here. 19 plus 1 is 20, so our state next is 20. On the rising edge of clock, the state next values will be transferred over to the state values, which means this will now become 20, and of course this will become 21. That cycle will continue on the rising edge of clock until the value of 60 is reached, at which point this reset circuitry activates, and it will cause the output to go to 0, which means state next, of course, goes to 1. One last comment about the hierarchical design and the fact that we've just described a logic circuit with 60 states. Few of us are going to build that using 74 series logic chips. Instead, you'll perform these functions using microcontrollers, digital signal processors, maybe a CPU itself, FPGA, maybe even ASICs. All of these devices can be described at a hardware level using Verilog, VHDL, and other languages such as System C. Not to be confused with programming languages such as assembler, C, Python, or dozens of other programming languages.